1 mole of ideal monoatomic helium gas in a heat engine undergoes the cyclic process shown in the figure below. The cyclic process consists of 2 isobaric and 2 isochoric processes. Analyze the graph to evaluate the efficiencies of the heat engine. The graph given in the questions is the P versus V graph, where the P is the pressure in ATM, not in Pascal, and the volume is in liter, not in meter cubes. There are 4 states given in the graph: state 1, state 2, state 3, and state 4. From state 1 to state 2 and from state 3 to state 4, these two are isobaric process, and from state 2 to state 3 and state 4 to state 1, these two processes are isochoric. The coordinates of the state 1 and state 3 are given. For state 1, the volumes is 1 liter and the pressure is 2 atm, and for state 3, the volume is 2 liter and the pressure is 1 atm. The gas in the heat engines that we consider in this question is 1 mole of ideal gas. So since this is ideal gas, that means it will obey the equations of state or ideal gas law, which is the PV equal to nRT, where the N is the number of mole and it is given as 1 mole. The gas in the heat engine is the monoatomic helium gas. Monoatomic means that the molar specific heat at constant pressure, constant volumes for this gas is 3/2R, where the R is gas constant, and the molar specific heat at constant pressure, it is 5/2R. According to the questions, we need to evaluate the efficiencies of the heat engine, which is denoted by the eta. By definitions, eta is the ratio between the output work and the QH. That means to find out what is the value of the eta, we need to analyze what is the output work for this cyclic process, and also we need to know for the 2 adiabatic and 2 isochoric process, which one the heat is flow into the system. Those flow into the system, after we sum it up, it will give us the QH. So now we need to analyze these two quantities separately in order to find out what is the value for the efficiencies of the heat engine. Now we start to evaluate the output work for this cyclic process that happens in the clockwise directions. The output work for this cyclic process is equal to the enclosed surface area. So that means it can be calculated by taking the differences of the pressure between the state 1 and state 4, multiply with the differences in the volumes between the state 2 and state 1. So here we will get P1 minus the P4. And for this one, we will get V2 minus the V1. So by multiplying these two quantities, we will get the surface areas of this square, which is enclosed surface of this cyclic process. Now we change the P4 to the P1. P4 and P1 is the same because from state 3 to state 4, it is the isobaric process. So we now change the P4 to the P3. And for the V2, we change it to V3 because from the 2 to 3, it is the isochoric. So V2 and V3 is the same. Now the reasons we take these steps by changing the P4 to P3 and V2 to V3, the reason is simply because the coordinates of the state 1 and state 3 are given. So everything that we calculate, we try to express it in terms of the coordinates of the state 1 and state 3. That's why here you see the subscript only, we can see the subscript only for 1 and 3. This is the work done, output work for the cyclic process, and it will take the positive value because this cyclic process happens in the clockwise directions. By checking the value of this P1 minus P3, we know that this one is a positive value. P1 is larger than P3, and V3 also is larger than V1. So this one also positive value. So that means after we multiply two positive value, then we will get the output work is the positive value. After knowing the expressions for the output work, now the next step is to evaluate the QH. But to find the QH, before we find the QH, there's one more information which is important and very helpful in our analysis. It is about the temperature of the 4 states. We at least, although we do not know what is the value of the temperature, but at least we need to know which temperature is higher, which temperature is lower. So to know about the relationship between the temperatures for the 4 states shown in the labels in the graph, the method is that we sketch the isotherms that pass through the states. Now for the state number 2, this is the isotherm that we sketch. This is the isotherm that pass through the state 4. So between state 2 and state 4, then obviously the state 2 is temperature is higher than the state 4. The isotherm which is located at the right hand side, the temperature is higher. Or we can know from this PV equal to nRT, the equation of state. From here we can change the T as a subject to get the PV over R, where we already substitute the N as the 1 because the number of mole is equal to 1. So that means since this R is a gas constant, so T is directly proportional to the products of the PV. Between the state 2 and state 4, then the PV for the state 2 is larger than the state 4. That is why T2 is larger than T4. So using the same method, we can check between the state 1 and state 3. We will see that the 1 multiplied with 2 is equal to 2 multiplied by 1. Therefore, this state 1 and state 3, they lies on another isotherms, same isotherm. They lie on the same isotherm. So that means T1 and T3, they are the same. And this T1 and T3 is the temperature is lower than the state 2, but is higher than the state 4. So our result of analysis about this temperature is this. T2 is larger than T1, which is equal to T3, and then larger than this T4. So that means among these 4 states, T2 is the highest in temperature, T4 is the lowest in temperature. Now we can start to find out what is the QH. Okay, QH is the heat flow into the gas for these 2 processes. For these 2 processes, which are 2 isobaric and 2 isochoric, some of them the heat is flow into the gas, some it is flow out from the gas. So we need to find out which process the heat is flow into the gas, and then we need to sum up all those quantity to get the QH. Now to analyze that, we need to apply the first law of thermodynamics, which is Q equal to delta ETH plus W, where the delta ETH is the internal energy change and W is the work done, Q is the heat. So for the state, from the state 1 to state 2, which is the isobaric expansion, the work done is positive because this is an expansion. Work done by the gas is positive. And because the temperature of the state 1, when it changes to state 2, the temperature is increased. So internal energy change would be a positive value in the process, because the internal energy depends on the temperature. When temperature increase means that internal energy change would be positive value. So based on the first law of thermodynamics, if this internal energy change is positive value and the work done is positive value, then of course the Q would be positive value. So that means the heat will flow into the system or into the gas in the process of isobaric when the state changes from state number 1 to state 2. Using the same techniques of analysis, now we can apply it to the state 2 to the process of state change from 2 to 3, which is the isochoric. Since the temperature is dropping, therefore sometimes we also call it as the isochoric cooling. And because this is the vertical line, there is no area under graph, so the work done is equal to 0. Another way of saying that is because there is no volume change, so the work done is equal to 0. And the temperature drop, it implies that internal energy change is a negative value. So again, apply the first law of thermodynamics. Since this is a second term, W is 0, internal energy change is a negative value, then of course the Q would be a negative value. So in this process, the heat is flow out from the system or from the gas. From the state 3 to state 4, this is the isobaric cooling. The temperature drop, therefore the internal energy change is less than 0, which is a negative value. And from state 3 to state 4, the volumes also reduce. So this is the gas will be compressed. Then the work done is a negative value also. Since these two are negative, so based on the first law of thermodynamics, Q also would be the negative value. Therefore, in the process from 3 to 4, the heat is flow away from the ideal gas in the heat engine. And from the state 4 to state 1, this is isochoric heating. Why it is heating? Because temperature is increased from the state 4 to state 1. So the internal energy change is a positive value. And again, because this is the vertical line, there is no area on the graph, there is no change of the volumes. Therefore, the work done is equal to 0. So based on the first law of thermodynamics, W equal to 0, internal energy change positive value, then the Q must be the positive value. So in this process for changing the state from state 4 to state 1, the heat is absorbed by the gas in the heat engine. Now we can see that the QH is contributed by the isobaric process when the state changes from 1 to 2, Q positive, and also the isochoric process when the state changes from 4 to 1, and this is another Q, which is a positive value. These two are positive. That means now we can know that the QH is equal to the summations of the 2Q in these two processes. This Q less than 0 and Q less than 0, these two processes we can put aside because it is not needed for us to find the value of the efficiencies of this heat engine. QH is equal to Q12 plus the Q41. And Q12 is the isobaric process. The Q, the heat flow into the systems, can be calculated by using the formula of NCP delta T from the process of 1 to 2, state 1 to state 2. And Q41, this is the isochoric process, and it can be calculated from the formula of NCV delta T for the process from state 4 to state 1. So we sum up these two, we will get the QH. But we know that N, the number of mole for the gas in the heat engine, is equal to 1 mole. Therefore, we substitute this N and N as 1. And the Cp value for the monoatomic gas is 5 over 2R. Cv value is 3 over 2R. Delta T between these two states is the T2 minus T1. Similarly, for the delta T from the state 4 to state 1, the temperature change is equal to the T1 minus the T4. We use the final temperature minus the initial temperature. But we need to change all the T in this line into the PV over R because we do not have any values about the temperature for the gas. We can change this T into the form of the PV over R based on the equations of state. Note that we already substitute the N equal to 1. That's why we have PV over R. And this T2 then of course is P2V2 over R. T1 is P1V1 over R. And for this T4 is P4V4 over R. Next steps, to simplify our equations, we cancel out the R in these two terms. So we have this. Again, same as what we have done for the output work. Now we try to change all these P and the V to the PV for the state 1 and state 3. So now this one, since this one is for state 2, P2, V2, now we change it to P1, V3 because P2 pressure for the state number 2 is the same as the pressure of state number 1. So P2 changes to P1. V2 changes to V3 because they are volumes are the same for this state 2 and state 3. And for P4, V4, we change it to P3, V1. Why? Because P4 and P3, their pressure are the same. V4 and V1, the volumes are the same. So now we have the expressions of the QH in terms of the P1, V1, and the P3, V3. Simply the reasons we express this QH in terms of all these PV of the state 1 and 3 is simply because these two coordinates are given in the questions. We can further simplify these expressions by factorize the P1 in the first terms and factorize the V1 in the second terms. So this is a QH that we want. It's a simplest form in terms of the coordinates of the state 1 and state 3. Now we can start to evaluate what is the efficiencies of the heat engine based on these definitions. Where the output work is this one, we already calculated, and QH is these expressions based on the result that we obtained just now. We can substitute the values at these steps, but if we substitute now, it will be difficult in the calculation because we will need to express or convert all the value or the coordinates of the state 1 and state 3 into the SI unit, which is Pascal and meter cubes. So it is a bit difficult to do that because the expressions for this eta is quite complicated. So what we do now is that we try to simplify these expressions by factoring out the P1, the terms in the numerator. We factorize, and for this denominator also we factorize the same things. Then the denominator here now will change to this form, and numerator for this will becomes the 1. So that means if we cancel, if we multiply this numerator and the denominator, which is the same, into this expression, of course we will get back the same things. By taking these steps, later we can see clearly that when we substitute a value, we do not need to convert this P and the V into the SI unit. This is the reasons why we take these steps. So after factorize, we have these two cancel out, then we will get this form. We can now start to do the value substitutions, where the P1s take the value 2, P3 is 1, V1 is 1 liter, and V3 is 2 liter. These P1, P3s are in ATM. So we do not need to convert it into the Pascal for the pressure. And this volume, we do not need to convert it into liter, because this is a ratio between the volume. This is a ratio between the Pascal, between the pressure. So the unit would be cancelled. That means if this one we put it in the ATM, this one also we put it in ATM, they will cancel out the ATM. This one, if we substitute in the liter, and this one also liter, they will cancel. But if we substitute the value at these steps, then we have to everything we have to convert it into the SI unit. That's why we take this step just now, so that we can. It is easier for us to do the value substitutions if we factorize this numerator and change this form into this form. The answer we obtained for these efficiencies of the heat engine is 2/13, which is 0.1538 and approximately equal to 15.4%.